Hello Legacy Sabers, Marsh here. So today we're going to talk about inverse functions. What you're going to want to have on you today are your notes and then a pen or a pencil. Learning targets for today, so what you're supposed to get out of this video. You can describe how to find an inverse. You can find an inverse given tables, graphs, or equations. And then also you can determine if two functions are inverses of one another. So now, here's what we're going to talk about. So functions. Let's imagine that functions are like the dye you use to color eggs. So we have a white egg, x, that's going to be put into the function, the blue dye, which we're going to just call b of x. Well, if I dunk a white egg into blue dye, I'm going to get a blue egg, right? That result is y. So if I put a white egg x into my blue dye function, I will get a blue egg. Now let's think about an inverse is what undoes that function. So how to inverse my blue dye function would be bleaching it, right? So if I undye the blue egg by putting it into bleach, I will get back a white egg. Same thing with inverse functions. So what we're going to be finding is an inverse function that will undo what the original function did. So let's take a look at the squared function. F of x equals x squared. If I put an x value, 3, into x squared, substitute it, I'm going to get 9 for my resulting y value. If I run that through the inverse function of x squared, which is the square root of x, I get 3. Again. Notice, guys, how from here to here, I got the same value because I ran it through the function and then I ran it through the inverses function. Same thing if I would do it with 11, I'd get 121. Inverse, give me 11. So what we're going to be finding is inverse functions. So here's the actual formal definition of an inverse function. The inverse function undoes what the original function did. If the original function is f of x, then the notation for its inverse is f inverse of x. So this right here, this little -1, this means that you are looking for an inverse. Now, this notation is important. You are going to see it like on a standardized test or something like that. So that way you know that that means it's talking about an inverse. If my original function was g of x, then it would have been g to the -1 of x. Something like that. A function takes an x value and produces a y. The inverse is going to switch this role. So basically, to find an inverse, all we're ever going to have to do is switch the x and y coordinates around. So let's think about this graphically. So if I have the point 4, 7, its inverse point is 7, 4. So all you're doing graphically for you to find an inverse is you're just going to swap the coordinate point around. Same thing, if I have the point -5, 3, you could have the inverse point of 3, -5. Now, I have y equals g of x. It has these points, so these are my dots from my table right here. My blue, the inverse, is g inverse of x. Notice, guys, how these two tables here are matching, except for the x values are now the y values, and the x values are now the y values. That's all you need to do graphically is switch the points around. X coordinates become y coordinates, and y coordinates become x coordinates. Now, where is this line of reflection? How are we able to know where it graphically would show up? Well, all it is the line y equals x. That's this line right here. That is actually called the inverse line. That's how you are known, or how you can find that where the line of reflection is. That's how the points would be reflected across. Let's take a look at graphing an inverse now. So I have the graph of f of x is given. We're going to graph f inverse of x. Here's what I like to do. I like to write my ordered pairs here in a table. I find it makes a little bit more sense for me when I flip-flop them. So I'm going to write my table down here for this guy. So my points, I got one at negative 3, 7, another dot at negative 2, 1, another one at negative 1, negative 1, and I got one at 1, 0, and then 1, 7. And so this is a parabola, equation of x plus 1 quantity squared. So now all we need to do is take that table that we just wrote down and then find the inverse of the other one. So all we need to do is write our table here, x, y, but instead of the y's being 7, 1, negative 1, 1, 7, those are actually going to be the x values for the inverse. So all this is doing to find our inverse is we're just going to flip x and y around. So then my x values for my original are now the y values for the inverse. Like that. Now let's graph those dots. So 7, negative 3, 7, negative 3, here's a dot right there. 1, negative 2, right there. Negative 1, negative 1, so it's right there. 1, 0, and then 7, 1. So if I draw that, there we go. Now notice, guys, how this basically is a parabola that's been laid on its side. That would be my inverse of that equation. Now, let's try just going from a table. So I'm going to create a table of values for the function f of h of x equals 2x plus 1 using the domain of negative 2, negative 1, 0, 1, 2. Now, that sounds really funny how it's asking, but all it's saying is using the domain. That means, remember guys, domain is your x values. So all it wants me to do is take these x values and substitute it in for x, find what you get out for h of x. So h of negative 2, so if I plug in negative 2, I'm going to get 2 times negative 2, which is negative 4, plus 1, negative 3. I get negative 1, 1, plug in a 1, I get 2 times 1, that's 2, 3, and then 7. Oh, no, hold on. That's 5. Can't math today. Now, let's create the table for h inverse. Well, all you need to do then is take my h of x, those are technically the y values, right? Those are just going to become the x values for my inverse. And then h of x, h inverse of x, that's technically the y, which is the x values of the original. So negative 2, negative 1, 0, 1, and 2. Now, how to write an inverse equation. All you're going to do first, you're going to switch the x and y around. So f of x equals 6x minus 12. Now it's going to become x equals 6y minus 12. All I did is I crossed out that f of x, made it y, and then I flip-flopped it around. Step 2, how to solve for an inverse. Solve for y after you switch-swapped. Let's complete that. So I have x equals 6y minus 12. Let's solve for y. Let's get y alone. Well, first things, let's add that 12 to both sides. That equals 6y. Now we need to divide by 6. So I'm going to give that 6 to both of them there. So I get 1/6 x plus 12 over 6, which is 2. And that would be technically equal to y, right? But now I wanted to find the inverse, so I need to make sure I use the correct notation. So all I need to do is just rewrite my equation and say I am finding f inverse of x. So this is just that notation piece of saying, yes, I did find that inverse and here it is. Let's try another one here. So I need to find the inverse of g of x. It's 3x plus 1 over 2. I'm going to find the inverse of him, so we're going to switch the x and y around. And then now we're going to solve for y. So we're going to get him alone. Well, he's a little funky here, so the very first thing we're going to need to do is multiply by 2 on both sides. Can't have that denominator there, so let's cancel that out. Get 2x equals 3y plus 1. We're still just solving for y, so let's subtract 1 using our literal equation skills here. Oops. 2x minus 1. There we go. 3y. And then looks like we need to divide by 3 to get y alone. So if I give that 3 to both pieces, that would be, I'm going to over here. So I got 2/3 x minus 1/3 equals what would be y. But since I'm showing that I need to find an inverse, I'm going to put g in -1 of x. Now, third topic of this video. How can I prove two functions are, in fact, no matter what, they are inverses? Now, in math world, it's not enough to say one leads to the other. So I can't just find the inverse of one of them and be like, hey, look, they look like each other. We need to have a method to show they're inverses. So to prove that two functions are inverses, we're going to compose them together. And we have to do it both ways, which means if I have one function named f and one function named g, we need to be able to compose f of g of x and g of f of x. If those two compositions here simplify both just to x, this means they are in fact inverses. If you have more than just x, they are not inverses. Even if you just do f of g of x and you get like x plus 3, that's not right. It needs to just be plain old x. Let's try a couple of examples here. So we're going to determine algebraically whether f of x equals 3x minus 2 and g of x equals x plus 2 divided by 3 are inverses of one another. So what we need to do is compose f of g of x and g of f of x. So let's practice our composition again. So remember, all this is asking is into f, we're going to put g, this guy. You're probably like, oh, Marsh, that looks scary. Into that, it'll be alright. Don't worry about it. So, into f, where we see an x, we're going to put this instead. So 3, I see x. So let's go ahead and write it out. X plus 2 over 3. And then minus 2, because we've got to finish off f. Well, let's see if this simplifies. So I have 3 times that, and then I'm going to divide by 3. So ultimately, this 3 and that 3 are going to cancel off, right? Because this is just multiplication, that's just division. So I'm going to be left with x plus 2, and then we got this minus 2 hanging out. These guys are going to cancel each other, and you're going to be left with x for f of g of x. That's good. We want just an x to be left behind. Let's try g of f of x. So that means into g, we're going to put whatever f of x is, which is 3x minus 2. Let's go ahead and do that. So I see an x, got to immediately put 3x minus 2. And then it looks like we got to finish it off. So add 2 and then divide by 3. So all I did is took f and put it in for the x. Well, this minus 2 and that plus 2, they're going to cancel each other off, right? Make me 0. So I'm going to get 3x over 3. Well, the 3's are going to cancel off, and you're left with just good old x. So notice, guys, how both the compositions turned into just plain old x. So what are these? They are, in fact, inverses of one another. Let's try another one here. So I have the functions f of x equals negative quantity x plus 1 cubed, and g of x is 3 plus x cubed. So let's go ahead and do f of g of x and g of f of x. Let's do this one. So into f, we're going to put g. So that means, if I do my substitution here, I'm going to put that inside of for every x. So, that's going to be negative, parentheses, so I'm going to start writing f. Oh, I see an x. Got to put g instead. So 3 plus x cubed plus 1 cubed. Cool. Let's try to simplify this inside. So 3 plus 1, that's like 4. X cubed. Cubed. Oh, that is never going to turn into just x, right? Like, that can't turn into just x. Because x cubed, and then I'm going to cube that again. So that's going to be like x to the 9th or something like that ultimately. It's going to be a really stupidly large problem, right? Something we don't even want to do. But we know, hey, that's never going to turn out right. This will never turn into what it needs to be. So we can definitely say not inverses at all. Not at all. And that's the end of this video. See you later, Sabers.